Okay, so here's an example drawn from a 3 by 3 matrix. So we'll have a little bit more to do here. Oops. Here's a 3 by 3 matrix A, and I'm interested in answering the question, what is a basis again, basis is really the star of the show here. What is a basis for the column space of this matrix? We can start by being really glib and say, well, we know exactly what a spanning set for the column space of A is. What set of vectors necessarily spans the column space of A? Without doing any work, we can answer this. Because it's the column space, a priori, it is the span of the columns of A. So that's a hasty answer, but it gives us a place to start. 1, -2, 3, 0, 1, 1, and 1, -1, 4. That's a spanning set for the column space. But in order to have a basis, we need that extra adjective. We don't want just any spanning set. We want a minimal spanning set. And so we need to know whether it's necessary to use all three of these vectors, or whether we might be able to throw one or more away. If we can throw one or more of them away, then we have to do that before we have a basis. We have to throw away as many vectors as it takes, such that we have exactly as many as we need to span the column space of A, and no more. So taking a quick look at the columns of this matrix arrayed as vectors in the XYZ space. Spin this around here and tell me, here we go. So if I look at these three vectors drawn in 3 dimensions, how does it look like they're arranged with respect one to another? Or maybe a more specific question I can ask is, what volume does the parallelepiped spanned by these 3 columns have in 3 dimensions? How could we answer that question, by the way? What quantity do we know how to compute that would answer the question, what's the volume of this parallelepiped spanned by these 3 columns? It's the determinant of this 3 by 3 matrix. So let's take a moment and reach back into our memory banks and compute the determinant of A. What's your preferred method for computing a determinant? I've got a 0 up here. Which, say again? Yeah, let's do a cofactor expansion. Let's choose for our cofactor expansion a row that has a 0 in it. That'll cut down on our work a little bit. So if I do a cofactor expansion for the determinant of A across the first row, then I'm going to get 1, the upper left-hand entry, multiplied by the cofactor of 1. And the cofactor of 1 is the determinant of this 2 by 2 minor. 1 times 4 minus -1 times 1. It's 5. And following that, I'll need, going across the first row, 0 times the cofactor of 0, but the cofactor of 0 would be the opposite of the determinant of this minor. So -1 times 3 minus -2 times 4, that's -3 plus 5, or plus 8 rather, 5. Obviously we didn't need to do all that work because we could have just written off this particular product because it has a 0 in front of it. And last but not least, we have 1 times the determinant of its minor there's its minor. Negative 2 times 1 minus 1 times 3, that's negative 5. And sure enough, we finish this determinant, and what do we get? So this 3 by 3 matrix has a determinant of 0. What are the consequences of having determinant 0? What does that tell us about the matrix A? A is not invertible. There's a key observation. And because A is not invertible, what does that tell me, if anything, about the columns of A? Right. Well, that's true too, but it's also true about the columns. So the columns of A don't all have pivots. There's at least one pivot missing. And because the columns of A don't all have pivots, what can you tell me about the homogeneous equation C1 times the first column of A plus C2 times the second column of A plus C3 times the third column of A equals 0, plus C2 plus C3 equals 0. What can you tell me about the nature of the solutions of that homogeneous equation?
Their coefficients are going to be non-zero numbers.
Right, that there exists some non-trivial solution of this homogeneous equation. Why? Because the missing pivot implies a free variable in the solution of any system, in particular the homogeneous system. And because the homogeneous system is always consistent in addition to a free variable implies infinitely many solutions. In particular, there are some non-trivial solutions. Okay. But if that equation has non-trivial solutions, that homogeneous equation has non-trivial solutions, what does that mean about the set of vectors A1, A2, A3? They linearly, say again? Dependent, exactly. So there's our crucial observation here, is that the 3 columns of this matrix are not linearly independent. They're linearly dependent. So, what that tells us about the span of these 3 vectors is because they're linearly dependent, at least one of them is redundant with the other 2. So we will be able to cross something out when we're determining our minimal spanning set. Because, going back to what we had started a moment ago, if what we're looking for is a minimal spanning set, what makes a minimal spanning set minimal is precisely linear independence. So we can replace this word minimal here with linearly independent, because that's a concept we can get our heads around. Oops. And to think of our basis, think of any basis, as exactly being a linearly independent spanning set.
But they're linearly dependent.
Well, that's just it. This example is linearly dependent. So this is not a basis yet. So the question of whether all 3 are needed is answered in the negative, because we found a moment ago that this set is in fact linearly dependent.
And why is it linearly independent?
Because this is what we want. Yeah, I should have made that clear. Is what we want is a linearly independent spanning set. And right now we have a spanning set, but it is not linearly independent, which means that there's some redundancy. And just like in our last example, any vector which is a linear combination of the others, in other words, which lies in the span of the others, can be thrown away. So now that's our goal, is let's figure out which of these three vectors we can discard without changing the span. And the answer to that is any vector which lies in the span of the others we can discard. But we need to figure out which of these three vectors belongs to the span of which of the other two. And the easiest way to do that is to, again, think back to that vector equation. C1 times the first vector plus C2 times the second vector plus C3 times the third vector equals 0. This equation, which defines linear independence or dependence for us, the nature of its solutions, tells us whether these vectors are linearly dependent or independent. Now, we said that there was not a pivot in every column. So there were some free variables which were causing this homogeneous equation to not have unique solutions. Let's suppose for a minute that C3 was my free variable and C1 and C2 were bound. Just take a guess here. Let's suppose this were the case. Then which vector could I get rid of in order to guarantee that the equation that results has a unique solution? Yeah. If I just ditch C3, if I ditch this whole term here, and I can ditch that whole term by ditching the vector A3. So if I forget that that term is there, then oops, get rid of the plus sign there too. Now this equation is going to have unique solutions because C1 and C2 are still going to be bound variables even after I get rid of the third vector and its free variable coefficient. So the point of finding a basis is we're going to take our columns, our vectors, and figure out which one of them corresponds to free variables and then just ditch the ones that corresponded to free variables. And once I've ditched all the free variables, now I'm going to have a unique solution to this system which gives us linear independence that we were looking for. Make sense? So that's our strategy, is to figure out which variables are free and ditch the freeloaders. So now the only question that remains is, how do we figure out which of our vectors is associated with a free variable? Row reduce. There's our tool. So let's just zip through this row reduction. 3, 1, 4. So when the row reduction dust settles, here's a pivot, here's a pivot. But the third column is missing a pivot. So which of these three vectors should I throw away? Let's throw away the third vector. Because if we throw away the third vector, the system, the vector equation, C1 times the first plus C2 times the second, will have a unique solution. And therefore, C1 and C2 are linearly independent. And C3 lies in the span of C1 and C2. So the conclusion is, to get a basis, we're just going to throw away this third column. And we still have a spanning set because the vector we threw away was just in the linear combination. It was already in the span of the first two. But now our spanning set is linearly independent. And therefore, the answer to the question, what is a basis for the column space of A, is answered by this set, which is now linearly independent and therefore has no redundancy in it at all.